Just a quick review of the whole idea behind finding real zeros of polynomials. And remember that what we're trying to do is find all the zeros of a polynomial. So here's an example of a polynomial. And the first thing we learned was that if you were to factor this polynomial, since it has degree 3, it has at most 3 factors. So, and we know that in the 3 factors, if we're going to get x cubed, each of those factors must have a leading term of x, because when you multiply these 3, you will get x cubed. But the really key idea here is that the numbers that would be in the place of these blanks where the question marks are, those numbers have to be factors of 24, which means that when you multiply these 3 polynomials together, the numbers that are in these question mark positions would be maybe one of them is 2 and another one is 2, and then the other one would be 6, I guess, because 2 times 2 times 6 would be 24. Or maybe one of them is 4, and one of them is 2, and one of them is, let me say, it'd be 8 times, 3. So that would be also a possible set of numbers that could be where those question marks are. And we could just try lots of different combinations, but we get quickly bogged down in all that work. And then the problem is compounded when the leading coefficient isn't 1, because then not only do we have to consider the factors of the constant term, we also have to consider factors of the leading coefficient, because again, if there are 3 factors for this degree 3 polynomial, then they must look like this, and that's the only way you'll get a leading term of 2x cubed is if you have a 2x and an x and an x. And again, if that's a 2, then one of these numbers has to be 2, but again, if this number was leading term coefficient was a different number, like 6, for example, then you would have other possibilities for what the leading coefficients could be in these 3 factors. But again, the 24 would have to be factored into these 3. So all of that said leads us to the rational zeros theorem, which tells us that if we want to know what the possible rational zeros are, and remember in class I said that the word rational should really be here, because this is about the rational zeros. Later on we'll learn about irrational zeros, and then when we extend the number system we'll get complex zeros. But for now, we're just looking at the rational zeros, and the only possible rational zeros would be fractions of the form of numerator being factors of 24 in this example, and denominator being factors of 2, the leading coefficient. And in general, the rational zeros theorem tells you that any rational zero of a polynomial is a number of the form p over q, where p is a factor of the constant a sub 0 on the end of the polynomial, and q is a factor of the leading coefficient of the term of highest degree. So with the rational theorem, you can determine what the possible zeros or the possible rational zeros of a polynomial are. Here in this polynomial, we have a leading coefficient of 1, and so the q values are plus or minus 1, and we have a constant term of 6. So let's see, we write down the p values first. P values are, well, I actually shouldn't put equal sign there. I should just say p. It's not, just erase it. There you go. So p, the p values are factors of 6, which are plus and minus 1, plus and minus 2, plus and minus 3, and plus or minus 6. So there we have the factors of 6. The q values, since the leading coefficient is 1, we just get plus or minus 1, so it doesn't really give us anything. The possible rational zeros, then, are all the fractions that you can write using these 8 numbers as numerators and then plus or minus 1. So you end up with just the same list as the list of p's. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those would be the only possible rational numbers that could be zeros of this polynomial. We'll do some examples, so I'm not going to work this one out and show you which of those numbers is the actual zero. The next one has a leading coefficient of 4 and a constant term of 36. So the p-values are all the factors of 36. And we did this one in class. I'm just going to get it started here. The factors of 36 are plus and minus 1, plus and minus 2, plus and minus 3, I shouldn't be using those commas, plus and minus 4, 36 has a lot of factors, plus and minus 6, plus and minus 9, plus and minus 12, plus and minus, well, you get the idea. So we get all those. The q's this time are factors of 4, which are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 4. Now when we form the possible rational zeros, we have a lot more work to do. The first p-value is plus or minus 1, and with the first q values, plus and minus 1, we just get plus and minus 1. We're forming all the fractions using positive 1 and negative 1 for numerators, and using positive 1 and negative 1 for denominators, because these come from our p factors and these come from our q factors. And so when we make possible fractions, we can use positive 1 with either positive 1 or negative 1, and that gives us plus or minus 1. And then we could use this negative 1 with either positive 1 or negative 1, and again, that just gives us plus or minus 1. So that's what this means. We're just making all the possible rational numbers with those two values. So we fix the p, and then we use all of the q's. So that's 1 with plus or minus 1, and now we're going to make all the possible fractions with the p-value plus or minus 1 with the q values plus and minus 2. So that's going to give us 1/2, plus and minus 1/2. Now we pair up the 1 with the 3 in the q list, and that gives us plus and minus 1/3. And now we use the 4, which is plus and minus 1/4, plus and minus. So now I've done all the possible fractions using the 1 in the p list with all the values in q, so now I'll go to the 2 in the p list, and so I'll get plus and minus 2. Now when I pair the plus or minus 2 from the p list with the plus and minus 2 from the q list, I just get plus and minus 1, which is already on my list, so I don't have to write it again. Next, plus and minus 2/3. And then finally, plus and minus 2/4, which is the same as 1/2, which is on my list, so I'm not going to write that one again. So you get the idea. I'll just do 3 for you now. So pair up the 3. You'll have plus and minus 3 when you pair the 3 with the 1. Then you have plus and minus 3/2 when you pair the 3 with the 2. Now when you pair the 3 with this 3, you get 1, which is already on the list. And so now the only other number we have to add is plus and minus 3/4. So if we continue in this fashion, we'll have quite a long list of possible rational numbers that could be zeros of that polynomial. Okay, so in the next example, we'll actually find the rational zeros and write the polynomials in factored form. Now in class, we did this using a combination of the calculator and the rational zeros theorem with synthetic division. So let's see how this would work. So first of all, we're going to write the possible rational zeros. And to do that, we start with the p's, which we've already got our list up above here, because this is actually the same exact polynomial as this one right here. So let's just look at the list we have so far and talk about this exercise. Now, we drew the graph of this, and we found out that when we drew the graph, we got a graph that looks something like this. It had n behavior like x to the 4th power, so it comes down, and it goes up, and it gets up pretty high. We don't know, well, actually, it goes up to 36 at least, because when x is 0, y is 36. So it goes up pretty high to 36. Then it comes back down. It's sort of symmetrical, and then it goes back up again. Remember, it has n behavior like x to the 4th power, so it's pointing up on the ends. So these are the 4 zeros. Remember, it has at most 4 zeros, and here they are. There's 1, there's 2, there's 3, and there's the 4th one. And by looking at our calculator, we can see that we have a lower bound here. I think that number is -3, and an upper bound here of +3. So we know that the zeros are between -3 and +3. So we were able to, after we made our long PRZ list over here, in this part, we made the whole list. After we made that list, we were able to eliminate a lot of possible zeros from our list of possible zeros by using our calculator. And we were also able to look at this x value here and determine that that was -2. So that means that we know that if we divide this polynomial by x plus 2, by x plus 2, we get a remainder of 0. So we did synthetic division, and we're checking for -2 as 0, which means x plus 2 is a factor. And we write the coefficients, and remember, there are missing terms here. So there's the degree 4 term. The degree 3 term has a coefficient of 0. The degree 2 term is -25 coefficient. The degree 1 term is also missing, and then the constant is 36. So when we do our synthetic division, make this double line here. Remember, we should get a remainder of 0 because we already know graphically that negative 2, oh, that's negative 2. So actually, x plus 2, negative 2, that's right. Negative 2 is a 0, so we're testing negative 2 in our division problem. So the 4 comes down, and then we multiply. 4 times negative 2 is negative 8. We add that to the 0, get negative 8. And now negative 8 times negative 2 is 16. 16 and negative 25 is negative 9. Now negative 9 times negative 2 is positive 18, plus 0 is 18. And then 18 times negative 2 is negative 36. Added to 36 gives me 0. So indeed, I get a 0. And now I know that x plus 2 is one factor, and the other factor, these are the coefficients. So the other factor is 4x cubed minus 8 minus 9 plus 18. So now I can use these coefficients, and I think we found that the number here was negative 1. Actually, that's not true. I think what we actually found was the number over here was 2. That's what we found. That was positive 2. So we can use positive 2 and use the reduced coefficients, the coefficients 4, negative 8, negative 9, and 18, because now we're going to factor that. So again, we set up our long division problem, and now 18 is our last number, so there's our double line. And 4 comes down. 4 times 2 is 8, plus negative 8 is 0. 0 times 2 is 0, plus negative 9 is negative 9. And negative 9 times 2 is negative 18 plus 18. Oh, what did I do there? Negative 18 plus 18. I don't know what I was writing there. 18, yeah, here we go. And that's a negative 18. That gives us our 0 remainder. And now we have the coefficients of the degree 2 term, because now we found that 2 is also a 0. So that means we have a second factor. We have x plus 2. And we also have x minus 2 as a factor. So I'm going to write x plus 2. My paper moved, so I'm writing it over here. And then x minus 2. Those are factors. Remember, x plus 2 is a factor because negative 2 is a 0. And x minus 2 is a factor because 2 is a 0. And now the third factor, these are the coefficients, but that's a degree 2. So let's write down that one. We get 4x squared plus 0x minus 9. So we can actually factor that as 2x minus 3 times 2x plus 3. There are other ways you can solve this or find the zeros, but now we can see that the zeros are from the first factor, 3 halves, and from the second factor, negative 3 halves. Oh, so that must be how Madeline got 2x minus 3 times 2x plus 3. I'm going to have to write it right here. So in class today, it was in the, I think it was in the afternoon class today, or maybe it was, no, it was the morning class, that's right. In the morning class, we did it a different way. In the morning class, we took 4x squared minus 9, and we set it equal to 0 and solved. So if you take 4x squared, I'll do it up here in blue. If you take 4x squared minus 9 and set that equal to 0 and solve it, you get 4x squared equals 9, and then you get x squared equals 9 over 4. And now when you take the square root of both sides, you get x equals plus or minus 3 halves, because the square root of 9 is 3 and the square root of 4 is 2. So now instead, the factors are x plus 3 halves and x minus 3 halves. Because if negative 3 is a factor, then x plus 3 halves, I'm sorry, if negative 3 halves is a factor, you know what I'm trying to say. All right, so if negative 3 halves is a 0, then x minus negative 3 halves, which is x plus 3 halves, is a factor. And similarly for positive 3 halves. So we get these two factors plus these two factors if we do it this alternate way. And I promised that I would think about this, a seeming difference in the factorization of this polynomial, which is a bit troubling because I also know that factorization should be unique. So I'm going to think about that a little later, but for now let's just continue going through and look at the next one. Actually, this next one says find the rational and irrational zeros of the polynomial, and I mentioned in class that this one doesn't really have any irrational zeros, so I didn't really do this problem in class, so I'll just help you work it out right now. Let's just find all the zeros that we can. So again, we're going to look at the list of p's and q's. P, remember, is all the factors of the constant 2, so the factors of 2 are plus minus 1 and plus minus 2. Q is all the factors of the leading coefficient, which is also 2, so plus minus 1 and plus minus 2. Therefore, the possible rational zeros are when you use your combinations of plus minus 1 with plus minus 1. Of course, you get plus minus 1. And then plus minus 1 with plus minus 2, you get plus minus 1/2. And now using the 2, you get 2 with the 1, and it's plus or minus 2. And then when you pair up the 2 with the 2, you just get plus minus 1, which is already on the list. So we have 6 possible rational zeros. Now again, we could use our calculator and do a graph to see if any of these are the ones that we should test first. So we'll just do that. So I just took a couple of minutes to graph it, and the graph looks something like this. So there's the y-axis, and there's the x-axis, and the graph has the end behavior, again, of x to the 4th power. So we know that it's going to come up, and then it comes through here, and it goes up, and then it comes back down, and then again it goes up forever because it's got the end behavior of x to the 4th power. Now I can see on my graph that this 0 is negative 2, and this 0 over here is 1. So I'm going to do synthetic division with 1 and find the other factor. So my polynomial is, let me raise this page up just a bit. My polynomial is, let me see, I'm checking 1, so I put 1 on the shelf. Coefficients are no missing terms, 2, 3, negative 4, negative 3, and 2. We'll get this set up. Okay, so bring this 2 down. So now 2 times 1 is 2, plus 3 is 5. 5 times 1 is 5, minus 4 is 1. 1 times 1 is 1, minus 3 is negative 2. Negative 2 times 1 is negative 2, plus 2 is 0. So now I have 2, 5, 1, and negative 2 for my reduced coefficients. And remember, those are the coefficients of the degree 3 polynomial. That's the quotient. The remainder is 0. And I've just shown that 1 is a 0. Therefore, I know that x minus 1 is a factor. Okay, I also know from my graph that negative 2 is a 0, so I'm going to go ahead and put negative 2 on the shelf. I want to find out what the quotient is. So the 2 comes down. 2 times negative 2 is 4, plus 5 is 9. 9 times negative 2 is negative 18, plus 1 is negative 17. This is curious. It's not working out. And yet, I see my graph is going through negative 2. So let me just check my work. Hold on. I just found my mistake. So when I did 2 times negative 2 right here, that should be negative 4. And 5 plus negative 4, that should be not 9 right there, but 1. And now 1 times negative 2 is negative 2. And negative 2 plus 1 is negative 1. That should be negative 1. And now negative 1 times negative 2 is 2, and 2 plus negative 2 is 0. So now I have the coefficients. It's a little messy because of my mistake, but I have 2, I have 1 right here, and I have negative 1. So now I know that I know that negative 2 is a 0, so x plus 2 is a factor. And the third factor is x, or what is it? It's 2x squared plus x minus 1. And now that part's quadratic, so when I get to a quadratic, I can use the quadratic formula to find the other 2 zeros. Because I found 2 zeros, I know there are 2 more, because look at the graph, there are 2 more zeros. Here's 1, and here's the other one. So let's see if we can factor 2x squared plus x minus 1. And I believe it's factorable. 2x, x I have to get a minus 1, so 1 has to be negative, 1 has to be positive, so I make the 2 positive, right, or make that one plus, that one minus, and so you can see I have now factored 2x squared plus x minus 1. So actually this one doesn't have any irrational zeros. All the zeros are rational, and in fact the other two zeros are 1/2 and -1.